All right.
Okay.
We're recording now. Yeah.
Okay. Okay, guys, welcome to another session of Book Club, Chapter 3. So do we want to do the questions that that's in the document first, or like?
I didn't had a chance to check the post if people already posted, or we can go through the flow and then take them
No,
up.
take more. Okay. Oh no, I thought like you had some notes. I thought you were going to go with that also. So.
No. So
And
I'm
maybe
preparing.
maybe we go over the
Yeah.
chapter first, and that's at the end we can.
Yeah, that would be
Okay.
good.
Okay. Yeah. So then let me share. So. Okay. Can you guys see the screen now?
Yeah.
Perfect. So I'll just do today's topic is SS tables and LSM trees. I think that will also lead us into B trees thing. Because based on my reading, I felt like only after reading all of these things, it made more sense. So last time we covered about like the basic log structured way of storing we discussed about log structured way of database, log structured way of storing the data, and how by storing uh, the storing them in the hash tables was like a little bit of advantage of retrieving the data faster. And we discussed, like we had like a lot of discussion about like advantages and disadvantages and all that stuff. So now let me go back to my notes. Actually, okay. So one thing that I felt interesting while uh, discussing about these things is like at the end of it, the author covered about the advantages and disadvantages of each of these approaches, and he moved into the next part of it, like this hash indexes and like how it slowly transitioned into SS tables and LSM trees and into the B trees. So I'll just hoping that we have enough context now on what we have discussed earlier. So I'll just say like some of the issues that were talked about. So in the log structure, we said like we're going to append to end of the file, keep appending to the end of the file, and then use that as a storage. So some issues that he talked about is like the format of the files. He talked about like CSVs is not the best format, and how do we handle the deletions, because what we followed in the log structured way is we keep appending to end of it, and so that we always have the latest. We start from the end to parse looking for the item, and when we find whenever we find a key, then that is good, that's the latest, and we don't really care about the old ones. And I believe we also talked about the segmentation of the files, right? Segmentation and compaction. I don't remember, did we talk about that, did we?
I don't think we kind of just touched upon it, but yeah, last time we mainly covered hash indexes and
Okay.
yeah.
Okay, so okay.
Or
Okay.
unless
Then,
I'm missing if something.
yeah. I think that's also important to understand, right? Before jumping into this one,
Yeah.
so I'll touch upon it. I don't know how much we discussed about it. So
Sure.
stop me anywhere and talk about it. So the way to improve all this, right? Instead of having like one single single file of data, he talked about like how that can be segmented. And the advantages of these segments is like you can keep working on compacting the segments in the backend, which is like we are adding, we are appending the key values to the file, right? So it becomes huge and difficult to manage. One is one of the difficulties, and second is also like by segmenting you get it's easy to access, and that's one of the advantages by segmenting the data. And also like you can, by appending to the end, we keep accumulating lot of duplicates to it, which is like the old history to it, whole history of the data, right? So by that, which is not really needed. So by segmenting it, what happens is in the back end, the segments can be compacted. Like we might be working on one of the latest one, and on the back end, the segments can be compacted by removing the duplicates, and then just maintaining the one unique key value, one unique key into the segments. That way we can have the sanity of the storage. That is one advantage. And when looking for the key values, you look into the current segment, and if you don't find it, you go backwards into the history. So that's one of the advantages of segmentation. So so that's about segment. So that's where he talked about file format, and he talked about deleting the records. So for deleting the keys, there is some way called tombstone. It's sometimes called tombstone, it seems. So whenever you want to delete a key, you can mark that in the file. We only append to the data to the file, but when you want to delete it, you can just mark it, and that can be considered in the compaction to not like maintain it at all, but just delete the keys. That's one of the things, right? We just talked about like retrieving the data and adding to the data, but there's also another thing that needs to be taken care. So he also talked about like strictly sequential, like common implementation choice would be to have one write thread. So one of the issues with this kind of log files is we need to always maintain concurrency control. So that means like only because we are just appending to the log file, we can only have one thread writing to the file, right? Because there's always like one file we are appending to it. That's one of the problems that we had. And he talked briefly about like how do we handle with the there are like crashes while you're writing, the system crashes while you're writing. How do you handle this? Handle those things. Okay. Okay.
So I want to add just one thing here. So the thing about concurrency control, I think it's an advantage that because it's an append-only log, so that's why even when you are writing, you don't need to apply reader logs.
You don't need to apply? What?
So see, I think there are two kind of log. So one is that reader is blocked when you're writing something, and another is that reader is fine to read when you're writing something. In this case, readers are free even when you are writing something. You don't need to apply logs.
Yeah.
Yes.
So it's an advantage, I think.
Right. It makes it simple. Yeah. True.
It makes it simple, but it's like you're throttling, right? So you only care about you can always write only through one thread. So
yeah, so there won't be any concurrency, like, you're just like writing append only, and there is one writer thread. So you're just like keep writing. And like, I think it was Abhishek earlier. So read threads are not blocked, usually trees or some other data structures, depending on how it's implemented. Sometimes we need to implement locks, based on data structure. Is like,
Yeah, I think the disadvantage of it is, suppose we have a powerful machine, right, with multi-core, but we have only one single thread to write, then
then we are wasting resources.
yeah.
So as per my experience, what I found is even if it is a single thread, it's very fast. At the end, the bottleneck is gonna come from the memory where it's writing, and it also simplifies your programming logic. But you can easily get hundreds of thousands of transactions per second if you are doing even on a single thread. I mean, because there is no overhead of the locks, right? If you are even if you are doing in a multi-threaded way, there will be somewhere a synchronized block, and then the cores are fighting for getting that access to that block, and they keep on shuffling that memory block in between them because it resides in L3 cache, right? But if there is a single thread, you get a kind of a help from the CPU that it knows that this data is being used over and over again, so it pulls from L3 to L2, L2 to L1, and it improves the performance significantly.
Why are we talking about L3, L2, and L1? This is not CPU, right? This is like IO thing going on.
Oh, no, I'm saying if you use multi-threads and single threads, right?
Yeah, but even in that case, right, when we're talking about multi-threading, we are talking about multi-threading with respect to IOs, right? So let's say underlying, since I'm writing to, in this case, I mean, I'm thinking that even though it's multi-threaded, it doesn't, it's more of an IO thread, right?
Okay, I was thinking like it first writes to the memory and then flushes those files to the disk, right?
Sure. That's true, but it won't be like a core, like it doesn't need to move to L1, right? L1 is when CPU needs to do some work on that data.
Oh.
All that's happening is it's going from memory, which might be DRAM, right? Like which is usually,
Yeah.
and then it's going to, there are multiple threads which are, I think what you probably are having in mind is like you're trying to map the thread to a CPU core. But I think that's a little different context when we talk about L3 to L2. We don't need to move it to CPU caches.
Oh yeah, I get it. I'm sorry.
Yeah. So yeah, but I think that's an important point, right? Even when we talk about multi-threaded writes, we need to keep in mind that when multi-threading is going on, even though you have multiple like threads working to write in parallel, but there has to be underlying storage also. Let's say we have multiple files, on which data is written. Then it kind of makes sense to have multi-threaded. But if we have one or like a contention or limited files, and you have more number of threads that are trying to write, they will be like, if there is locking and all this involved, there will be an overhead coming from that. So it's not just about maximizing your throughput because of multiple threads, but we also have to take into account the extra tax that we have to pay because of the locks. And in this case, I think that point is simplified. So if you have one writer thread, so
Yeah.
And this thread is in thread allocated for IO.
yeah.
Okay, and there could be multiple threads. And L1, L2, L3 caches come into picture only at the CPU having multiple.
Yeah, like anytime L1 and L2 belongs to a core, right? And L3, so if you have a system like your laptop, then you have, let's say, 4 cores, right? So each core will have its own L1, L2 cache, which are very small in size. L3 is shared among cores, right? And then there is another level of like memory stuff coming in. But the point I was trying to make is anytime, let's say I need to run some processing on my data, then it makes sense. Then data needs to be moved from, L3 to L2 or L1 because CPU needs to work on that data. In this case, all we are trying to say is we want data from memory to disk, right? So
Right.
I was saying that even if it's an L3, we probably don't need to move it to L2 or L1 because CPU doesn't need to work on it.
So L3 is like RAM. RAM falls into L3 or?
That is another level, but L3 is also one higher level. Like it's memory, of course, but it's faster in the sense that it's also a reserved section, but shared among cores and faster than the core, other parts of memory,
Oh,
which is accessed by multiple, all applications.
okay, interesting. I'm sure I heard about these things, but have never went into the
Yeah.
details. This is a good discussion. Good, thank you.
A quick question on the single write thread. Would that be a bottleneck somehow? Because let's say, we have like, this set of data to write, right? Now we have like many set of data, right? It's still, the speed of write is still the same, right? So that will be queue somewhere, that will be make the write slower, right?
Yeah, but I think that's where we have this partitioning and all these things come into picture, right? We don't want to write. I think then it will become like each partition will have one thread where we know that each partition will be append and it will be independent to the other partitions or other segments or other files, right? If you are using one single file, then
Yeah.
that becomes a contention. But if you divide it into multiple files and maintain a index of those files in a different place, then that doesn't become a contention.
Are you saying if we have multiple file, each file can have one write thread?
Yeah, I mean,
Yeah.
like the reason why we are maintaining one thread is because we want to append to the end of it, and we don't want like multiple things trying to append the same thing or
Yeah.
like one overwriting one over the other.
Oh,
So if there are multiple write threads, right, and you're writing to a single file and you're trying to append it to the end, right? The end is at a given point, it's like one point. And all threads are trying to write it somewhere. Either you have to implement some locking mechanism so that one writes and then it gets updated and then next position is available to the next writer thread. Like if all try to write to the same location, that's not going to work, right? So
okay, yeah.
that's where.
I think this is like very basic level of structure that he explained. I
Yeah.
can go into details on like how to handle all those kind of things.
Right.
Okay, so he also talks about like at first glance, just appending to the file always seems wasteful because we are having all this duplicate values stored, which we really don't need. So merging and sequential write operations, which are generally fast. But he says like these are much faster than writing to the random locations. It seems.
Yeah.
So that's where it has advantages. And even when something crashes by something fails, he says like you don't have to worry the case where value is being overwritten, leaving the file containing parts of old and parts of new data. So I think this is just talking about advantages of just appending instead of replacing the old values, because anyway the old values are not needed. And that limitation is overcome by doing the compaction of the segments on the back end, right? So
Yeah, like the space overhead is,
yeah. Merging old segments avoids problems of data files getting fragmented over time. I know there is this fragmentation mechanism which plays a major role, but I'm not quite sure about it. If somebody has an idea of like, I know like whenever something is written into the memory, it is written into like probably 4K or some chunks of data, and if it doesn't fill that chunk of data, the memory is left empty, and then that could over the time that could go wasted unless you defragment it. So that's what I understand by this fragmentation, defragmentation. But he talked about like Okay, I think I got it while I'm talking about it, but so yeah. So I think like when we keep writing to the memory, right? So what we are doing by compaction of the files is like we divided the files into multiple segments, and when what we do is like periodically go and merge them and remove the duplicates and write to a new file and delete the old files. So while writing to while we were creating those old files, we would have had like a lot of memory not used completely. Like we wrote only the fraction of the 4K size that can be written, right? By combining those things, we have actually, every time we compact those files, we create a new file. By combining those files, at least to a certain extent, we have also done the defragmentation of that memory. So that's one advantage, which otherwise, like we could, by leaving them all there, we are actually wasting a lot of memory, which needs to be defragmented. Okay.
Naga, do you wish to say storage, because we are talking about files? I mean, defragmentation of the storage.
So I think two levels, right? From what I understand, storage is like directly what we see, but also like when we write to the memory, you don't write to like every byte, right? So you actually write like chunks of memory, like 4K, 4K, and if the data doesn't fill the 4K, you still allocate that 4K. I don't remember exactly how
Yeah,
much.
but I think, Naga, like the fragmentation aspect that we're talking about, all this compaction, that's talking in terms of the underlying storage, the file,
Right.
not like the hash map or the memory stuff.
Yeah.
Yeah. And that actually ties to one of the questions. I don't want to just, jump on that, but just as a pointer, we have a question coming up on the shared doc about what is the difference between on-disk structures and memory, right? So that is like one of the points there. But yeah, we can take that up later. But I think the fragmentation, from what I understand, the fragmentation concept is talked in the context of disk files.
Yeah, disk files. Yeah.
I will just like to add.
Yeah.
I will just like to add one point here. Typically, in our operating systems books, we would have read that normally fragmentation is of two types: internal fragmentation and external fragmentation.
Hey, can you guys hear me?
Hello.
Yeah. Yeah. Yeah, I can hear you.
Your voice is breaking.
So typically in our OS books, we have read that fragmentation is typically of two types: internal fragmentation and external fragmentation. And I think the reference here is probably of external fragmentation, because you haven't found the block of that, the contiguous block of that size. Even though small blocks additively can add for that. So I was just trying to relate to that fragmentation.
Yeah, yeah. I think that's what it is. Okay. I think he discussed about that a bit more in B trees. So let's, yeah, when we get there, probably we can discuss again on that. Okay. So, sorry, we're still in the hash indexes. So he talked about some limitations with using the hash table indexes, which is like hash table index must fit in the memory. Otherwise, you'll have like hash collisions and you have to fiddle with it. And with this hash tables, there is like, if you have range queries, which is like I want to get the data between this key to this key. You cannot easily scan over all the keys between. You'll have to. Okay, so I think he's talking about, like, to set us for the next topic. He's talking about the range queries. Like these keys are not like random keys, right? These keys are not in any order or anything. But if you have a query of like you want to get the data from key 1 to 100, then you will have to. It's not sorted, so you have to randomly go read and multiple times. So that's one disadvantage he talks about, but that again depends on like what kind of reads that you want to make on it. So if you want to make such kind of range queries, it's a challenge is what he's talking about. So that leads us to our topic of the day, which is SS tables, which is called as structured storage segments. Each log is a structured storage segment, which is called SS tables. Log precedence of the same key, apart from that, the order key value is, it doesn't matter.
Sorry, hey Naga, Abhishek, I had to drop out of because there was some audio issues. One of you make me co-host. I said both of you as host before leaving.
Oh, okay. Let me do that. Abhishek, are you there? I'll
Yes.
continue with the discussion. Can you help with that? Can you make?
Yeah, sure.
Thanks. Okay. So the idea here is like, so far what we have stored in the hash is all like not sorted, right? So there are some disadvantages to it. So the idea here is like sort them. By sorting them, you have the advantages of like, while you are, like I said earlier, you're doing the compaction of the segments. Earlier, because it was not in a sorted order, the compaction becomes a little challenging. So you can use merge sort kind of an algorithm, which makes it faster. And also reads become easier once you sort this data. Because you know that is sorted, so you know like how to search for the items and like move along. So those are good advantages of having them in the sorted key over having not sorted, directly writing them. But okay, but we have this challenge of whenever you add the file, you have this challenge of like making sure it is in a sorted order, right? So to do that, to maintain the sorted structure, he have suggested using some tables like red-black trees or AVL trees. With that way, you can, I think when you use one of these trees, I think when you read back, you can read back in the sorted order, or the way stored is also in the.
Yeah, I mean, I don't know much about them if anyone has details, but what I gathered was you just write in whatever order you want, but they kind of do the operation of, sorting the data internally and manage so that when you read it back, you will get it in sorted order.
Yeah, they just do a in order traversal. So everything is in the line. When you have to write, just do in order.
Okay.
Yeah, so my understanding is, so basically you need a binary search tree so that you can look for the keys in login, right? But if a binary search tree is queued, so let's say if all the keys are in one line, then you will take big of n. So the advantage of red, black, and AVL trees, they keep the tree balanced when you are adding nodes so that it will take log n.
Right. Yeah, I understand. But in terms of like sorting, I think the key point is to maintain it as a binary search tree and do an in order. Yeah, and a balanced one, like you said, because that will make it,
Okay. So the idea is to use those red-black trees or AVL trees. So make it like a balanced binary tree. So it becomes, the reads becomes faster. And by making them sorted, we have made the compactions faster by merge sorts, by taking the overhead of making them sorted. Okay. So
there is one other advantage I want to highlight about the sorted tables. So if we go back to our discussion from last week, where we were talking about the, pros and cons of hash map, in memory, that hash map index. The things we raised was, what if hash map gets, how to control the size of hash map, right? So that it can stay in memory. And the idea there was about maintaining a sparse index, right? Rather than having one entry in hash map for every unique key in the file. What if you use this sorted tables underlying in your storage, then what you can do is rather than having a dense index, you can have a sparse index. And sparse index means that you can just maintain pointers or you can just maintain entries in your hash map only to a subset of keys rather than to all of them. So that will help you save the space for in-memory hash map. And you can only do that if your underlying data or the pointers, that is sorted.
Okay. Yeah, the sparse.
I think there was,
sparse
yeah,
index.
because the idea is when you maintain a sparse one, as I said, you are only maintaining key value pairs for only, let's say out of 10, you're only maintaining it, let's say for 4, keys. The question is, what happens when the user tries to read a key, which is not in your hash map, right?
Yep.
Then how will you locate it? But because of this sorting idea, you just get to the key, which is, like the closest to that one. And then from there, you get to the segment. And since your data is sorted, you can do a binary search on it and just locate it there.
Okay.
Yeah.
Yep, that makes sense. Okay. So I think the one issue he talked about with this approach is if database crashes and you lose all the by maintaining this. I think we are still right now we are only maintaining this sparse index in the memory, right? Sparse index. So I think what he talked about is like if the database crashes, you lose this in memory.
Contents of hash map.
Yeah, all the contents of hash map. So
hey Naga, can you scroll up a little bit where you can see the advantages?
Am I sharing my book actually, or am I sharing the?
You're sharing the notes like that website thing.
Okay. I mean, like I was looking at the notes. I really don't want to share it in the hall. So, okay.
Yeah.
I mean, scroll down. I mean, yeah, scroll
Okay.
down where you see the advantage. Yeah, that's good.
Okay.
Yeah.
Okay. So merging the segments is simple, efficient. No longer need to index all the keys in memory. What DP was talking about, like maintaining the sparse index, and that makes it reads faster. So those are the ones. So I think at one point what he was talking about is like even in this case, you still maintain a log, write ahead log.
Yes.
Kind of a write ahead log. In case of crashes, you still maintain like the append kind of a mode log to recreate this index whenever.
No, so that is write ahead log only actually. It's not like append only is not another category.
So I think write ahead log is kind of a append only log, but you just right. Okay.
Yeah. I thought you were saying another level of logging. So yeah.
No. Write ahead log to maintain this in-memory hashing that we have.
Yes.
Not so Naga, I think it's probably for this red-black tree. So red-black tree, it's a in-memory data structure. We cannot create red-black tree in the hard disk. So the red-black tree is also, whenever we are inserting something in the red-black tree, we maintain a append-only log. So that, and what we're doing is when that red-black tree becomes bigger than a particular size, then we write that to the disk and flush our memory. So while we were maintaining the red-black tree, if our machine crashes, our red-black tree will be lost. So that's why we are maintaining this append-only log.
Yeah, but what do we mean by, so I think this, so when we say append-only log, where is it maintained? It's on disk?
Yeah, append-only log is maintained on disk because.
Right. So my point is that write-ahead log, it's just a term, right? Write-ahead log is maintained in an append-only manner. Like it's not like two different things. The idea, the way I got this was talking about hash map, right? There are two aspects we need to consider. One is if there is a failure, right? Your hash map is lost, and that will impact two things. Now, when the system comes back and there are reads happening, there is a read request, you first have to build hash map again, right? That is more like, okay, you can always, like as a naive approach, you can read the segment files and you can capture the unique keys and whatsoever. You can build this hash map again,
Yeah.
or you can maintain a snapshot of hash map in the disk and just read it through. So that is one idea. But
Right.
what I was touching on was that, okay, like you have new data in your hash map that's not yet written to the disk, right? So if that gets lost, then how to handle that? And my thinking is what you are saying, append only log and write ahead log. They're actually referring to the same thing. Append only is a technique, right? How you are you overwriting or appending? But write ahead is just a terminology.
That's right. I think what Abhishek is talking about is what do we store in that log? Is it the red black tree that we talked about, or
No. So I think the thing is, it comes back to the point of in-memory data structures and on-disk data structures. So the question is, when you're maintaining a red-black tree or some sort of structure in memory, now you're right that you can't just directly write it to disk, but you need, and that's where there is, I think in the future also, there's another chapter to it, which talks about how to map your in-memory structures to your disk structures. So you can't just directly write them through, you're right. But that would be another area where the question is, how do you map your red-black tree? Because they are totally different concept, dealing with pointers and whatnot in memory. But that's...
Yeah. So one thing, I think whenever a new record comes, we need to do three things. So first thing, we need to add it to our red-black tree, which is in-memory data structure. Second thing we are doing is on disk, we are writing it to append only log. And third thing we are doing is we are updating our hash map if we need to update our hash map for that thing. Right? So we are doing these three things. So a write operation is converting to these three operations.
So why the hash map?
So there is no hash map as such.
So go there,
I
please.
thought that we either need red-black tree or...
No. Oh yeah, sorry. So basically, whenever in memory, you can only retain only certain amount of data. So when you have a certain limit, so like 20 MB, 30 MB or something like that. So if it goes beyond a limit, you flush that to the that sorted string table format and you write it to the disk. But what happens is when it hasn't reached that limit, but now the system has crashed, what will happen to the data that has accumulated in that time period? So for to handle that itself, they have kept that write ahead log just to handle that only specific segment itself.
Correct.
So whenever a new write comes, they write it to write ahead log, and after that they insert into the AVL tree or the BST format, and that's it. So after it gets flushed, we remove that. We don't need that write ahead log file as well.
Yeah,
so
we can truncate it. Yeah.
Okay, so the advantage of maintaining this this sorted AVL tree was reads were faster, right? Reads are faster, and
I think it's self-balancing, right? Like it could maintain the data in sorted order regardless of how you write it, right?
Yeah. I mean, like we want to maintain it so that our reads can be faster.
Sure.
Yes, Naga, this AVL tree is just for the memory only, for mem table. When writing to the SS table, so that is a sequential write in a sorted order.
Correct. But the point was, I think what Naga is asking is, what was the rationale? Like we were initially using hash map. Now there are a couple of combinations here. One is you can maintain both hash map and AVL trees, or you can just maintain one of them. Of course, leaving the disk structure, the sorted.
No, that AVL tree is to keep your data sorted in SS table.
Yeah, and you're using hash table for searching for keys which might not be in your AVL tree or right, because AVL tree is only for some like 20 or 30 MB of data, but your key might not be in there. So then instead of going to the log files, you can use the hash map to find that key.
So that hash index is actually to your SS table segment.
So let me explain. So there is no hash map as such. So in memory, you only keep that AVL structure, and when it is written to the disk, you write that all the keys that were accumulated in a sorted format.
Yes.
And so that will be like a log file itself. And we actually maintain two more files that has a Bloom file and as an index file. That index file has that key to offset thing. So whenever you need a key, you check in the Bloom file or that index file.
Yeah,
to know whether that
that's like a hash map. Like if you want a point query, right, where you're like, okay, here's the key, give me the value. That's where this index and the file you're mentioning or hash map idea would help. But
no.
Yeah.
This is not the idea I'm saying. This is the actual internal representation that is used by Cassandra.
Yeah. I'm not saying idea in terms of abstract idea. I'm saying like the main takeaway, right? Why we need certain data structure versus other.
So Naga, I think we have moved on from the hash table to SS table, right? So I think this is a different topic, and this has, as per whatever we are seeing on the screen, it is using only the trees.
No, I think there is a little confusion here. This is not about, we haven't moved from hash table to SS table. SS table, we are talking on disk, and hash map, all the discussion we were having was for memory. So these are like, we haven't really picked one over other there.
Okay, we don't have a hash map, right? Look at the second point of the advantages. Let's say no longer need the hash map in there. Right?
No, that is true. It says no longer
need hash map.
No, it says
wait. So this is
keep in mind that it says that for all the keys.
Yes.
We still need the hash map.
Yes. So
no, you are like Uday say, right? You only need the Bloom filter. The Bloom filter is like a hash map, but it's not telling you where the reference to the address. It's just tell you, okay, whether the key exists or not. Let's answer true or false.
No. So I think we are directly jumping to Bloom filter. We should really slow it down. We suddenly Bloom filter in, which we didn't even talked about right now.
Yeah, but that Uday was mentioned about it, right? That is kind of like, how do you know if the key is present in your database or not?
So you're right, Leon. Bloom filter is the right idea there, but I'm just saying it for the sake of, there's a lot of confusion about SS table, hash map, Bloom filter, AVL tree. So I think we, if we just kind of lay it out, otherwise it will become like the concepts are right, but like does one of you want to go over and just
but okay, so
one question, can I ask everyone one very simple question? So we are saying that we are keeping everything sorted in the disk, right? Now, are we saying that keeping things sorted in the disk, let's say if we don't have hash map or something, we can search for a key in logarithmic time? Are we saying that?
Search where?
Not really.
Not really, right? Exactly. That's the point. So that's why we still need hash map. So the advantage of keeping the things sorted in disk is only that when we are doing the compaction will be faster because it is merging. But if we have to look for a key and the key is, let's say, not on hash map, then still we will have to do a sequential lookup.
No, it depends. Abhishek, we can do a logarithmic lookup because the data is sorted. When you look to the segment, right, the key is not in hash map. So you find the closest one and then you get to the segment, which possibly will have the key. Now, because the data is sorted by keys there, you can do a binary search.
No, DP author clearly mentioned that if your data, your record is a constant size, same size, then you can do the binary search.
Sure. That's true.
Yeah. What if your record is in the file you already saved on disk? You cannot do binary search on that, right? Because periodically you have to flush that tree, map to the file, right?
No, Leon, if your record size is constant, then you can jump, say like if your segment size is say like 1,000 bytes, so you can directly jump to 500 byte, then to 50 byte
Right.
offset.
And the other thing is, I
But
think
there
what
could be
Leon,
multiple files. How do you know, what file we go to, and how
right,
do you
so
know,
So that information will come from the hash table or hash
yes,
map.
yes.
Right.
Like if you bring up a picture, Naga, from the book, I think we are running out of time.
Yeah, yeah.
There's
I mean, like,
a book which talks about Sparse.
good. I think that's I mean, like, I really don't want to share the book.
Okay.
Just for the copyright reasons, right? We don't want to
Okay.
share the book. So, I mean, like, we can draw a diagram and see. I think that's a good discussion. I think what author tried to mention here, or like wanted us to understand here, is what is write effective and what is read effective, and which one we need to pick, whether SS table versus B tree. I think whatever the discussion that we are having is really what he wanted us to understand, which makes us understand which is write efficient and which is read efficient, and how the reads and
Or
writes.
how to make them one, right?
Yeah.
Like what are the strategies?
Right. So I think based on the discussions, I'm still not very clear. I believe maybe we can continue this discussion next week, or like someone can take the ownership and can explain all of us with a couple of scenarios.
That's how I'm laying out my slides.
Okay.
Scenario.
So Naga, I mean so if someone has the doubt, so it will get cleared if you think about that. What was the issue in the previous approach? What we were doing. So here in the new approach, we are just trying to resolve those issues.
Right. Yeah. Yep.
Good point.
Yep. Good
yes,
point.
at the same time, in the previous approach, we discussed, we say, we cannot keep the hash map in the memory because it's so big.
So that's why the new hash map is not for all the keys. It's a sparse.
Yes.
Sparse.
Yeah. Maybe, let's maybe stop here if that seems okay. And
yeah.
I see there were some questions posted on the shared doc, which is really good. That's how we want to keep it going. So I would say let's continue that, even based on today's discussion. And, for others, like it is good if we post it, as soon as we can, so that rest of us can also see the questions and we can possibly, add or stuff here. So some things can just get cleared based on some information that we can post.
Okay. So, Deepi, can we do this? Actually, just because we had a very good discussion on this, how do you want to make sure, like, we have if somebody wants to take ownership and explain to everyone on like what's really happening in this area?
Yeah,
I think I can explain if you want on a whiteboard like next week.
Yeah. Do we want to set up
so
like sessions before our next week, or I'm just trying to get.
No, so one of the things I'm doing is I'm preparing slides which go scenario by scenario. Like, given the scenario, what are the limitations? Okay, how do we handle this? So how about I share that with you all? And then if that seems good enough to, maybe we want to follow that kind of pattern, right, in our discussions. And I'm also like writing blog posts, so we can also, use that as the platform.
So maybe Abhishek and you can work together, and like we can have one session specifically for this area just to understand, and we can I'm thinking, like, should we have it before the next book club so that we can also continue on the book? I don't know how it works for everyone. Just a random idea.
I'm not sure in terms of the timing, like, but we can maybe sync offline and brainstorm how we can approach it. Or if anybody has ideas here, feel free to chime in.
Just the question is, should we do it in the next book club session, or like Should we?
So you want to, so what you're looking for is summarizing, like laying it out in a very, like, you know, whatever we discussed so far, right?
Right. Just to.
Yeah. So I think as a first step, let me share the slides. I think that should help.
Okay.
But also, yeah, if Abhishek, you know, you want to summarize, I think once things are summarized, they won't take much time.
Yeah, no, I was thinking summarizing reading we are doing that's written in book, but if we can actually see, like if we can actually write some code or like draw diagrams on how what are the things happening in memory, then we can better understand.
Yeah.
So that's
Yeah.
Okay. Sounds like let's discuss the same topic in the next session, book club session.
Yeah.
Either in the meantime, DP will share those summary slides so we can go through this. And
yeah, let me know. I think
spend some time in the next session also if that's not clear.
Yeah, sounds good.
Yep, cool. I think we have another session in 5 minutes. So